Tonight we're going to look at an overview of the FRC robots, just sort of in general, kind of what the subsystems are, how we sort of construct them with the different parts of them, or different like systems within a robot. Then we'll be able to use this knowledge to be able to dive down deeper in the future as we start talking about how we actually build them and how we choose to design and how we make a lot of those design choices every year when we get a brand new game. So a lot of this is going to be very general and just talking about FRC robots as a whole over years and years of various different games. Okay, so each season we get a rule book. So that happens on kickoff, right? That first Saturday in January. We're giving the game, but we're also giving all the rules that our robot has to meet. And so there's a lot of restrictions on exactly how we're able to design and build certain parts of the robot. So we normally get some sort of max starting size. So in some years it's a length, width, and height. Some years it's a frame perimeter. So it's like you'd like wrap a string around your robot, and that string can only be a certain length. And then you also have a height limit. You normally have a maximum weight, which recently it's been 125 pounds. That doesn't include the battery. That doesn't include the bumpers. Some details in there. But that 125 pounds is what we're kind of like building towards as our max weight that we're allowed to hit. The robot normally has some ways that once the match starts, it's able to expand, or there's some limits on how it's able to expand. So it may have certain height limitations that it's not allowed to reach higher than once the match starts. So it has like a starting height, but then it can extend stuff up to a certain height normally. And then sometimes it also has a limit to how far it can extend stuff out. So big reasons for this is you wouldn't want to allow robots just like be able to block off like half the field or something. If they were able to expand the full width of the field, which is like 27 feet, you could do really, the strategy for other teams, and you just wouldn't be able to play the game nicely. So they try to make limits on the robot so that everyone can actually play the game. There's detailed specifications for the control system and the pneumatic system, so all the electrical parts and the pneumatics, which we're going to talk about in a little bit. And then there's a lot of safety rules to make sure that the robots that we all put on the field and every team competes with is safe for the students to be around and the volunteers at the event, and also safe for the other robots. So you're not just absolutely like destroying or messing up the other robots too badly. They're definitely allowed to interact, but we're not trying to destroy anybody. Each FRC robot, if you've seen like the ones that we've built, we've been in through the lab, they all look very different. And so that's basically because they're all designed to play a very specific game. So a robot from one year is not going to look like a robot from a different year because they're just going to have very different tasks that they have to do based on that game. And so as you start looking at more robots, you start knowing the different games from various years, and we'll go through them. I've been sending out videos like every week from like different games, and we'll still keep doing that. You'll be able to pretty easily identify which game a robot was built for. So if you see a random robot, you'd be able to say, oh, that was built probably for the 2017 game or something, based on how it looks, what it was able to do, what the mechanisms are or the subsystems. You can start figuring out what the robots can do based on the tasks it had to solve, which are all unique to each game. Okay, the ways that we control motion on the robots, there's two main ways, one of which is motors. So we have a variety of motors we're allowed to use on the robots. On our Thursday times when we talk about controls, we'll have another session where we delve deep into exactly how we control the motors, some of the differences in the types of motors, why we choose one or the other, and a lot more of the details. But for now, the important bit to know is that motors just allow us to have very easy rotary motion. Motors, like you would expect, they spin very quickly, which is useful. And then we use gears and belts and other things to get them to a speed that we want them to be able to be more useful, which we'll talk about more in another session as well. And this is important because they use the power that's inside the battery to create that motion. So we're limited on how much energy we can basically use in the match based on how much energy is stored in the battery. And we're required to all use the same type of battery on every robot, and you're allowed one battery per match. So that's one of the big limitations of FRC is how much energy you actually store in that battery. That's how much you can use during a match. The electronics are the control system that handles control of all the motors and handles distributing power to each of the subsystems, their motors, any of their sensors, anything else that's helping control the robot electrically. So that's what all the electronics are doing. This is sort of the most basic FRC wiring. We went over a little bit of these components a couple Thursdays ago if you were there for that, and we'll do it again for sure at some point. Um, but this is kind of what an FRC electrical wiring kind of looks like. This drivetrain that's here, these wheels and everything, this is called a kitbot. I'm about to mention that again in a slide or two. But this is kind of the standard FRC drive that comes in what's called the kit of parts every year that you're allowed to just like, you have the option of getting. So a lot of teams end up using this, which is very helpful, especially if you're a new team or a young team, or just a team that you don't want to spend your resources designing the drivetrain. The kit of parts drivetrain is really, really awesome, and this is a good picture of one, and we'll talk about it again in just a little bit. Pneumatics are the other easy source of motion for FRC. So instead of rotary motion that we get from motors, pneumatics very easily give us linear motion. So you can see in this little animation down here. Pneumatics use compressed air. So this item right here is called a compressor. It takes air from outside the environment and it forces it into our storage tank, and it forces it to build and build and build up pressure. And the normal air that we're breathing and walking around in, we're at, we call that 0. So that's 0 PSI, however you want to call it. And that's our normal. So then we compress all the way up when we're storing it, all the way up to about 120 PSI, pounds per square inch is what PSI stands for. Don't worry too much about the details right now. We'll cover that all later. But you just kind of know some of what the terms are and that you've heard them before. It'll help as we go through and get into more and more details as we're learning. And then when we actually send it to this thing called a cylinder, we're able to direct where the air goes. So just like in this animation, when we push that pressurized air into the rear of the cylinder, it pushes this rod forward. And when we push air into the front of the cylinder, it brings the rod back. So we get that nice linear motion that's super easy to control. So we can have two very easy positions. We have an all the way back and we have an all the way forward. So if we just need something to move into two positions, pneumatics works super well for that. They're very easy to control. They're very reliable, and they're just another source of motion that we can use, and especially for little small things. If you just need something to move like a small amount, pneumatics are great. They're relatively lightweight, and we use them on robots all the time for the robots we design. Okay, so we divide up when we're kind of designing and when we're thinking about FRC robots and just robots in general. We're going to kind of divide them into what we call subsystems. They often can be called mechanisms, but it's just some way to categorically describe each like section of the robot instead of having to like think of everything of it as a whole. So we can break it up into different parts easier so that multiple people on our team can be working on different parts of it at the same time. If we didn't have subsystems, it'd be really hard to just like contemplate and design every bit of the robot if everyone was working on the whole robot at the same time. But by being able to break it up into chunks, we can give it out and assign different roles to people. We'll have various students leading each subsystem, and they'll be in charge of making sure that subsystem is progressing and getting designed well and tested and all of that throughout the year. And each season, those subsystems kind of get broken up a little bit differently based on the game tasks, because the games are different every year. But no matter what, we'll have some number of subsystems. Most robots have anywhere from like on the low end, if it was a rather simple robot, somewhere around 4-ish maybe, all the way up to like 7 or 8 on some pretty complicated robots. But some of those might be kind of minor or smaller subsystems as well. So the rest of this presentation, we're basically going to talk about a lot of the example subsystems from various games, and most FRC subsystems kind of fit into these. Each year, they'll kind of have different names based on exactly what they're doing in the game. I'll kind of refer to them, but they all are somewhat in the range of these of the subsystems we're going to list out tonight. So the first subsystem, and by far the most important in nearly every game, is the robot's drivetrain. So the drivetrain is how the robot actually moves around the field. It also includes sort of the main frame of the robot normally, or the main structure. So this is that same kit of parts robot, kit drivetrain, whatever you want to call it. The last few years, it's been a version of this thing called the AM1 It's made by Andy Mark, which is the AM part, and then 1 for you is supposed to be like if you made those the words ONE for you, is in like everyone gets one. 4 because this is the 4th version of it. The majority of teams I don't actually know if the majority of teams use it. The majority of teams definitely should use it. It's a 90 to 95% level drivetrain to where like everything for most things you need to do on your robot for the robot that season, the kit of parts drivetrain does them and does them pretty well. And the big advantage is you don't have to spend resources designing and building it because they basically get this kit you get the kit at the beginning of the year. You cut a couple things and then you basically just assemble it per the instructions. So this is the drivetrain that's used by the EveryBot, which is a project run by the Robonauts alumni and some other, and there's Mary from Spectrum helps with it, and a few other alumni from other teams. And they basically design a robot that they give the entire plans for to every team, and it uses the EveryBot. So this is the robot that we built for. We've had a version of a simple robot based on this chassis the last 2 years that we've had parts of our team, especially a lot of the new students build, and we'll do that again this season. So that's what 8515 will be running through, is building a robot that runs on this kit of parts chassis, and then has a version of kind of the EveryBot mechanisms on top of it, or subsystems on top of it. And it's a really good introduction to how robots work because they have that kind of plan and everything laid out. Here are a couple other pictures of our drivetrains from previous years. So this is our 2017's robot drivetrain. This is our 2020 robot drivetrain. And we're about to go through a couple of some different descriptions of types of drivetrains that exist in FRC. But again, the important thing to remember from drivetrain, it's the frame of the robot, it's that main kind of lower frame, and it's the part that gets the robot moving around. So it's really important that that is reliable and works every match. If your robot can't drive, if everything else is working on your robot, but you can't actually move around, there's very few games where you're going to be able to score points and be a productive member of your alliance if you can't actually drive around. So your drivetrain is super important to get right. That's one of the best reasons to use the kitbot, is it just sort of works, and it's very, very solid. We've been around long enough that where we can build our own drivetrains, and there's advantages to it, and it's not super resource intensive. We have enough people who can do the designs and the build and everything where we're not sacrificing that resource. But for a lot of teams, this is definitely the right way to go. Okay, so talking about a few different types of drivetrains. So by far the standard FRC drivetrain, and what all three of these pictures are what's called a tank drivetrain or a skid steer drivetrain. They're kind of interchangeable. There's a few other terms too that you might hear thrown around. But the basic concept, and it's used in most robot drivetrains. If you've ever built a Lego robot or a Vex IQ robot or a Vex robot or FTC robot, most of them are the same type of drivetrain where you have a left set of wheels and a right set of wheels, and you control the speeds forward and backwards for them, so that when both sets of wheels are going forward, the robot goes forward. When they're both going backwards, the robot goes backwards. And when they're going in opposite directions, that's how the robot's able to steer and rotate. So when the right side is going forward and the left side is going backwards, the robot rotates to the left, and the opposite's true to go to the right. You'll sometimes hear a term, if you start doing some of your own research and looking at things, you may hear a term called West Coast drive. West Coast drive is a type of tank drive. A lot of people can argue over the exact definition of what West Coast drive is, but no matter what, it's a type of West Coast drive. It has some other characteristics, or it's a type of tank drive. It has some other characteristics that are important to get there, but it's just another term you'll see. But the kit of parts drive is not a West Coast drive. That is not true. But a West Coast drive is a tank drive, if that makes sense, and how you categorize it. It's like a subsect that has some specific requirements as well. The next type of drivetrain we're going to talk about is a swerve drivetrain. So this is what we've just started working with this season. So this past spring, we built our first two working swerve drivetrains. So there's one, this was kind of the prototype one that we were able to test with, and then we built the full one for 8515's Robot Gamma Ray 2021 that we took to the Texas Cup this summer. So swerve is very different from tank. So tank and skid is kind of like the simplest and most standard sort of drivetrain. Swerve is a very advanced drivetrain. It requires a lot more motors, so it needs 8 motors. So you have 2 in each corner of the robot. On each one of these modules, so this is called a swerve module, one of the motors is driving the wheel and spinning the wheel to actually give it rotation, so you can actually move around. And the other one is just rotating this whole lower assembly to point the wheel in a certain direction. So kind of like the caster on a shopping cart or on a rolly chair, where the wheel can spin around and kind of point in any direction. This is a similar thing, except it's just powered. So we can tell the wheel which way to point, and we can tell it how fast to spin forward or backwards. It is more complicated, so it definitely takes more. It takes a little bit more effort to get working and to get working well and to get working reliably. But the big advantage of it is you are able to move in what's called omnidirectional motion. So that means we're allowed this robot. So depending on which way you want to call forward, so we can call towards this like Clorox wipes bottle forward. This robot can move forward and backwards. It can move left and right, and it can spin, and it can actually do all of those things at the exact same time. So we're able to like have the robot spinning while driving at an angle or any direction we want simultaneously. So this allows us to have a pretty useful advantage to being able to line up to certain targets very quickly. So if we have a small target where we need to like hang a game piece or we need to score in a small slot, we can be rotating and like aiming to that position while driving to that position at the same time. If we miss a little bit, if we're lined up a little bit off to the side, we can just like kind of slide to the side and get lined up. We'll have more videos and photos and all of this as we go more in depth in the future. But so this is what we've started using. There's a lot of reasons why it became more advantageous to do swerve this season and this next season in 2022 that we're not going to go into right now. But we're going to see a lot more teams kind of going to the swerve direction in this 2022 upcoming season, and more as we keep going. Okay, so these are the two kind of drivetrains that are largely that we would most likely ever build. So there's disadvantages and advantages to each of them. But almost every robot pretty much every robot we've built that we've actually competed with has been a tanker skid steer. And then 2021 we just built swerve, and we probably will do it again in 2022. So these next couple are largely just so you can identify them on other teams. We likely will never actually build one of these for a competition robot. They all have weaknesses that aren't that are very rarely going to be overcome by what their advantages are. So one of those drivetrains is called a mecanum drivetrain. So mecanum drivetrains use mecanum wheels. So this is this wheel right here on the left. They have rollers going along the wheel at 45-degree angles. And this allows them to be an omnidirectional drivetrain similar to swerve, except the way the math works out, you're not quite getting the same amount of power from the motors as you're driving in each of the directions. So as you're going left to right, your speed and power are different than when you're going forward and backwards. Same with you're trying to like rotate while driving. And there's a lot of disadvantage to using it. Quite a few teams still use it. It ends up not, in general, it's not as good of an FRC drivetrain as it is for some of the lower, or not lower, but smaller robot divisions. So FTC, which is smaller, 18 by 18 robots, Vex Robotics, which is a competition of similar size, those make a lot more sense the way their fields are foam tiles instead of carpet. There's normally not as much pushing and shoving around as there is with FRC robots, where these drivetrains don't normally excel as much as the two options we presented earlier. Similarly, you have a lot of the same disadvantages from Mecanum that you do from this next type of drivetrain, which is sometimes just generically referred to as an omnidirectional drivetrain or an omni-wheel drivetrain. Sometimes called an X drive, because you have the wheels here pointed, like the motors kind of make this X here, because each wheel has to be at the corner for this to work with 4 of them, because the rollers on these wheels are at 90 degrees. Sometimes if it only has 3 wheels, so you can imagine if the wheels were just at a triangle to each other instead of in the corners of a square, but they're in the corners of a triangle, then it's sometimes called a Kiwi drive. Again, you kind of have some limited traction and pushing power. And there's some very unique applications where this is beneficial. Most times, neither of these are going to be your optimal drivetrains for FRC, but we will see them on other teams' robots, so it's useful to know that they exist so we can identify them and kind of know what's happening with them. Okay, the last two types of drivetrains we're going to talk about is a H drive. So this is a kind of a variation on a Omni or X drive, where instead of having the wheels in the corners at an angle, you have a normal sort of tank configuration where you have these four wheels all lined up in a straight line so they can drive forward and backwards, but you add a fifth wheel in the middle that allows you to slide side to side. In theoretically, this is omnidirectional too. You could be driving forward and sliding sideways and turning all at the same time, but it's really tricky to make sure that all five wheels are actually like touching the ground at the same time. You can imagine if you had a five-legged table with one leg in the center, it'd be very easy for one of those legs on any corner to not be touching the ground, unless they were all like perfectly flat or had some way to spring or give or anything like that. So this isn't used as often to get full omnidirectional, but it is used to be able to just like slide sideways sometimes when the game calls for it. But it is tricky to do well, and it's not a drivetrain we'll likely build, but you will see it on other teams' robots. So again, it's useful to know what it is. And the last type is kind of just I'm just grouping a bunch of different drivetrains together, but some teams will try to combine versions of these to get sort of the benefits of both types. So in this picture right here, we have these four mechanism wheels in the corners, but we also have these four regular wheels, and these little cylinders up here are pneumatics, and they're able to push up and down on the wheels to change their positions. So they're able to swap between either these mechanism or mechanism wheels on the ground or these regular wheels on the ground. So they get the goal is to get the advantage of both a mechanism drivetrain and a regular tank or skid steer drivetrain. This ends up normally being heavy. It normally ends up being difficult for the driver to know when to switch and how to switch to use it well. And so you don't really necessarily always get the advantages of one or the other. You end up with some middle ground. It's normally not ideal for most applications. So the important thing is just to know that these exist so that if we're looking at them, when we're looking at other robots and talking about them, we can see that they are using these drivetrains. But largely for our robots, we're going to be staying inside of one of these two options, unless some very unique circumstances happen with a game that really pushes us to some other role. Okay, so moving on past drivetrain, some of the other subsystems on the robot. One of the ones that gets overlooked by far too many teams because it's absolutely critical, and only 1 year in the past 2 decades have we not had to build bumpers, which was 2015. Every other year, robots are required to have bumpers. And bumpers are kind of, you can imagine them just like the football pads for the robot. They would allow our robots to run into each other, hit each other, push each other, without causing lots of damage. So they take any of those big impacts, and a lot of the energy just gets pushed into compressing the pool noodles that are inside of here. So it's literally just plywood, pool noodles, and a fabric covering. The colors match your alliance, which we talked about earlier. So this is also how we know the kind of like the jerseys for the robot, so we know which side each robot is playing for during the match, which is very helpful. They also have your team number on them, so we can identify whose robot is what during a match. They're very easy to see and pick out the team number that way. A lot of work goes into making sure how the bumpers actually mount, how we're able to swap them in and out quickly. Make sure they're actually going to be robust and stay together throughout the whole match and throughout the whole season. So making sure you actually design and plan for your bumpers from the beginning is very useful and something that not a lot of teams do. So this is always part of this is largely normally part of the person for our subsystem leads. Whoever's the subsystem lead or leads in charge of our drivetrain normally also are in charge of our bumpers, and so they design them all together to make sure the mounts and everything work. Okay, so moving on past the sort of drivetrain and bumpers and moving up to our much more game-specific mechanisms. Almost every robot's going to have a drivetrain and bumpers. But as we get into our game-specific mechanisms, these are where they start getting, a lot of them are very different from each other. But a lot of games, you do need some way to pick up game objects from the floor. So sometimes the game objects will start there, so there'll be certain starting positions where there's game objects already on the floor. Other times they'll be there from either other teams dropping them or missed shots, or human players throwing them into the game field sometimes. But a lot of games, the vast majority of games, have some sort of floor intake that's designed to pick up a game object and then allow the robot to manipulate it in some way for it to then score points with it. Most of the time, we're going to try to do this with rollers or wheels of some sort. So this is our 2018 robot. It had to pick up a, the game piece was called a power cube. So it was like a milk crate wrapped in a fabric. And so it had these wheels. They're actually like different types of wheels. That was actually important for exactly how to make it work. But it was able to spin these and kind of suck the cube into here. These are both pictures from 2020. So these are the actual 2020 competition and then a prototype intake as well. So this had rollers. These are just like polycarbonate plastic tubes that ran. So we spun these. This version had wheels on the first roller and then rollers going up the rest of the way. So as these spin, the balls are able to kind of get sucked up into the robot. And then we can store them and get ready to do the rest of what we need to with the balls, or whatever the game object that year is. So it might be inner tubes, it might be cubes. We've had plastic gears before. We've had really big balls, we've had really small balls. It all just depends, but most of the time we're going to use some sort of roller or wheels to suck it up off the floor, or to, I guess, bring it up off the floor. We're not using suction, but we're just going to bring it up off the floor and get it into our robot. Another type of intake, and it kind of depends on the game and how it's set up, is a human feeder intake. So some games will have a human feeder station. So this was a 2017 game, and we had these slots that the robot could drive up to. And then one of our drive team members, the human player, could slide the game object down that ramp and into our robot. So we had to make sure that we designed the kind of chute portion or ramp portion well enough so that when the object comes down the ramp, it's able to go into the exact spot we wanted in our robot. We don't drop it on the floor. We don't miss it. We make it easy for the driver and the human player and everyone to do the task well of getting that object into our robot and ready for us to use when we go and score it. And so this will happen in multiple games. There's often, even in ball games or any other ones, there'll be ways to for the human player to pass game objects into the robot. The next thing in a lot of games, it just kind of depends on whether you have allowed to hold multiple objects or a single object. But in games where you're allowed to hold multiple game pieces, you normally need some way to sort and store those game pieces so that you're able to actually have them all ready for you to score when you need to. So a lot of times we'll call it a hopper or an indexer. And the main purpose of this is just to sort of get the objects ready and funneled in to, like in this case, we want them funneled into like a straight line. So then we can push them all through the launcher and launch them out of the robot, which we're going to look at in just a second. But there's other times where you may just have them stored, so then you can pick one, or you can pick them off of your robot and then put them somewhere else. So really the hopper indexer is just anywhere you're going to store the game pieces and organize them before you actually go and score with them. So this is most common in ball games where we have where you have multiple balls and you have to sort them. But this could happen in any game, depending on what the game designers decide to give us for rules. Just like if we had this game where we had to pick up these cubes. This game we were only allowed to hold one cube at a time. If they gave us a game where you're allowed to hold multiple cubes, we'd have to figure out a way to build a storage location for multiple cubes that we could then sort, or we could then grab from and score from. Okay. Wheeled launchers. So these are pretty common. We've launched game pieces starting back in like 2006 was the first game where we had to like launch balls through the air. We've done it on quite a few occasions since then. We've also had a frisbee launching game in 2013. And so with that, most of the time the concept is going to be pretty similar in that we're going to use a fast spinning wheel. So in this picture, this is our 2017 launcher, and we have these 4 wheels right here that we spun up very quickly, and the balls were fed through this belt. So this was like our hopper indexer on that robot, and they went up some more rollers, and they came out of this slot right here, and they went into the goal. This is the launcher on our 2020 robot. These wheels right here spun up very quickly, and the balls came up, rode along this path along the back, and then launch out into the goal like we see in this video over here. And so we do that a lot in various launcher games. If I had to guess, I would say we probably aren't going to get another launching shooting game in 2022 since we just did this same one for the last 2 years. But we really don't know. The game design committee could give us anything on kickoff in 2022, and we'll have to play with it whatever it is. But it's unlikely that they just kind of give us the same thing. They do try to add variety in most years, but it really just depends. They could, by giving us kind of a similar thing, it might be that they're kind of tricking us because everyone's not expecting it anymore. Okay. The other way that we often launch objects, and it kind of depends on the game specifics again, is some form of catapult. So this video over here has our 2014 robot catapult. There's also a picture of Jersey Voltage's catapult from that year, and they're kind of built differently, but they both kind of do the same thing. These are normally best in games where you're only allowed to hold a single object at a time, so that it's not so your reload speed isn't a problem. You can imagine if we were trying to shoot or launch 5 balls like we do here very quickly, it would be much harder to do that if we had some sort of catapult mechanism, because we'd have to like reload the catapult every time, put a ball in, fire, reload the catapult, fire, and it would just take a really long time. So most games where we only have a single game object you need to launch, and then you have to go like collect another one, so you have time for your reload, the catapults work really well for that. There also can be much more compact. So we see a lot of catapults in the 2014 game here. We had this really big ball that we had to launch through the goal. We also see a lot in the 2016 game, which a lot of the robots needed to be really, really flat to go under this low bar, which was one of the challenges your team could have done. And so catapults worked with that because you could make a very compact mechanism in terms of catapults. A lot of times the catapults are going to be powered either by springs, where you have a motor kind of pull something back. You pull a spring down really hard, and you have a mechanism that releases it, and you release all that stored spring energy very quickly to launch the ball. You can also, there are ways to make pneumatics fire very quickly to launch the ball with a catapult as well. So this robot here in 2014, our robot was a pneumatic catapult. It's using pneumatics to fire the ball. This 4587 robot, Jersey Voltage, they were using springs and a motor to pull back against the springs and then let it go and fire the ball. The next type of subsystem, and these are kind of like the two most common kind of game types, are often some game where you have an elevator game where you either have to lift and move objects like we do here in these images, or some type of ball or launcher game where you're throwing objects into a goal. So in the elevator games, you have to build some form of an elevator most of the time, because you basically want to be able to take and score on various scoring heights. So in this 2019 game, we had these hatch panels, and we had to score them either on the low rocket, middle rocket, or high rocket. So we needed a mechanism that was able to raise up and down and position those panels to the right heights so we could drive in and score them. We also had to do the same thing with those cargo balls, those big orange balls. So we had the same um, low, middle, and high, but they were actually different locations. They were different heights, so we had to make sure we could program that as well. Yeah, so it's kind of like a forklift where it's able to move up and down, just straight up and down very easily and very nicely. The other way to sort of move up and down and to get things lifted into the air is to have a robot with an arm on it. So this is the CAD model of our 2018 robot. So we had this arm right here. This was the intake. And so here you can see it actually picking up those cubes. So it's able to score, and then it's going to come over and it's going to pick up one of the cubes. It's going to lift the arm up, and it's going to score it again. So an arm in general is just a part of the robot that uses rotation to lift something up and down. You'll see some robots with much bigger arms. Maybe the pivot will be higher, and they can reach a lot higher with the arm. It all just kind of depends on what the game, what's needed for the robot to play the game well. Wrist is kind of similar to an arm. It's basically just a small arm, but really it's another place that we're able to do some sort of small amount of rotation to do some part of the game. So here we have to raise and lower our intake. So it has to start inside what's called a frame perimeter, and then we're able to lower it down to intake the balls, and then we can rotate it back up to store it away or to make sure we're in the starting size. Sometimes it's a little more complicated than just like pivoting up and down. Sometimes you'll have what are called linkages, so you can get slightly different motion, but it's all kind of doing the same thing. Our 2017 robot here, we have a video of it where it's going to score the gears. It drops down. This little intake, the video is not exactly easy to see. It sucks it in, so there's a wheel that pulls that gear in, and then it's coming over here to score it. So that was another version of a wrist. So a lot of times you'll end up having some type of wrist mounted to a elevator or mounted to an arm to sort of change the orientation of the game piece before you go and need to score it. So a lot of times some of these will be combined, and it just sort of depends on exactly what the game is and exactly how you're designing the robot. Do you make one or the other, or what do you call it, and all sorts of things like that. But they're all kind of the same thing. One of the last subsystems is often for the end game of the robot competition, so or for a match. So at the end of the match, normally the last 30 seconds or so, a lot of times the robots will be able to get points for how they're able to position themselves at the end of the match. And so one of those things is climbing. So this happens really regularly. Multiple of the past 5, 6, 7 games have required the robot or allowed the robot to get more points by climbing some structure at the end. These are all photos from 2020 where we had this hanging bar that was able to tilt back and forth. And so you got points if your robot was suspended from the bar, and you got more points if the bar was level. So if there was like another robot over here that could balance out the bar, you got even more points. Very commonly, the climbers end up being similar to the construction of the elevators. You can imagine they're kind of the same thing. Elevators normally need to move up and down a little bit faster so you can get to the scoring points. The climbers need to be a little bit stronger or be able to lift more because they have to lift the entire robot instead of just the game piece. So sometimes you have to balance that while you're doing your design. So you make sure because sometimes you try to make them do both. That was really common in 2018 where you had your elevator also be your climber. And so this type of mechanism works well for a lot of climbing tasks. There are other climbing tasks. So we had, there's climbing tasks where you use like a winch where you somehow deploy a hook and then you have a motor that just spools in a big cable and pulls the robot up once it's hooked onto something. The 2017 game here, I don't know if we can actually see it in this video, but there was like a rope that you would drop down and the robot would grab onto that rope and climb up and hit a platform or hit a little button to know it was climbed. The 2019 games, the robots had to lift themselves onto these platforms, so you didn't have anything above you. You had to like push down from the ground to be able to get up. Um, so the climber tasks can all look a little bit different each year depending on how we're climbing. But that's one of the subsystems that's pretty common is some sort of end game climber subsystem on most robots, or a lot of games will allow you to build one. And then one of the final types of subsystems we're going to talk about tonight is the field manipulator. So a lot of times in games, they'll have very specific elements that you need to build your robot around to interact with the field in some way. Where these things basically don't really make sense unless the field actually exists. You can't really use them. If you just have the game piece and you're like practicing in the hallway, the field manipulator stuff doesn't really work or make much sense without those field elements involved. 2012 and 2016, we had two different field elements that were like ramps or bridges that we had to tip down. So here we had this whole arm was able to bring down these sort of like teeter-totter wedges, and we'd use pneumatics to bring the whole thing down, and then the robot would be able to drive over it. The same type of thing happened in 2012. You had this big bridge that you had to lower to your side so your robot could drive on, and they could drive off the other side. 2016 also had a few other, there was called defenses that year. It was like a whole castle theme. So there was one where you had to raise like it was called the portcullis, but it was like a big, one of the fences that moved up and down. You had to be able to raise that for your robot to go under it. There were a couple different doors that you could try to open with your robot so your robot could go through it. And so a lot of teams built various mechanisms to sort of interact with those field pieces to allow their robots to play the game better. 2020 had a unique field manipulator method, which was the control panel, which we've seen when we watched that animation, where you have to turn the wheel with the different color patterns on it to turn it a number of times or turn it to a certain color. So teams would build a specific mechanism to do that spinning of that control panel to manipulate the field and get more points that way. Okay, so those are pretty much all of the normal subsystem groups, and almost every subsystem on a robot's going to fall into one of these categories somehow. One of the things we run is a mechanism library, mechanisms.spectrum347, and it has a lot of various examples of these robots. So if you want to sit through and look at example robots from previous years, this is a really nice way to do it. A lot of them are categorized. We need to go through and categorize the last couple years. We've been behind on doing some of that. So if anybody wants to help tag some of the photos and learn how to do that, let me know. Okay, let me bring that back up. Okay. So this has a lot of the various mechanisms from different years. You can go through and see how teams were climbing or their drivetrain, different intakes, all of those types of things. You can see a wide variety of how teams build them. So we kind of categorize them all as the same thing, but they're not going to all look the same at all. So some teams, there's wheels and belts and rollers and all sorts of ways to sort of intake and do similar tasks of just like bringing the balls into the robot or launching the balls out of the robot. There's a lot of different mechanisms to do that as well. So looking through here is a really good way to get some understanding of how robots operate or how they look. If you have questions, if you want to just post one of these photos in Discord or Slack and ask questions about it, that's a really good way to get happy to answer. Other students on the team are happy to answer and get more of that knowledge as we're going through and kind of doing some of the design work and getting to the point where we will be designing robots designing and building our own robot in 2022 when we build the new one for this new year.